Hello, my name is Nguyễn Đăng Vinh Quân, a student in class of 2025, and this will be my brief presentation on my final project for the computer organizational computer organization course. So this will be my camera, and so this will be my screen. So I'll switch between the two. My product is called the Pet Care Simulator, inspired by many pet care simulator games that are on the market. The most prominent one, I think everyone knows this, I hope so, is the Tamagotchi. It's a small egg-shaped device with three buttons and a screen. The pet is on the screen. It displays the status of the pet, and you can either feed pet it. And if you don't take care of it and it leaves you or dies, and then it's game over. Another very famous similar is the Talking Tom series, where on the screen there's a cat or a dog, and it can mimic your voice. Like you say something, and it says back in a funny voice. You can pet it, you can feed it, you can play with it, etc. So think that this could be a very interesting product that I can implement with the simple circuits in Circuitverse. So this was my inspiration to do the product. And now I'll go through the design process for the product. The first ever design of a finite state machine consisted of 5 states: happy, sad, hungry, sick, which is a combination of sad and hungry, and then finally game over. Mm, there are four inputs. Two of them are user generated inputs, which are feed and pet, indicated as P and F here, F and P, and two clock timers to indicate that the like uh, to indicate the state transition to the next state. If the one for the hunger and one for the happiness, if the clock timer runs out, then it signals a transition to the next state, like something decreased. So first the pet starts at happy, then if the clock signal for happiness expires for E, and it becomes sad. Similarly for hungry, if you feed it, then it becomes happy again from hungry, and from sad, if you pet it, it becomes happy again. Similarly from sad and hungry, if you become if you let the pet become if you let the pet gets hungry twice in a row, then it immediately game over. Similarly for sad, if it is sad, then it gets hungry, then it becomes sick, and then if it's hungry, it gets sad, then it also becomes sick. If it's sick, then either it gets happier, it gets hungry or unhappy, then it's game over. But I quickly found out that with 5 states, meaning that you need 3 bits for the state representation, and for inputs, which makes 7 inputs for the state transition diagram, as state transition truth table, and 128 rows of truth tables is not fun to do and very time consuming. So I decided to simplify it and make it so that there's only 4 states and 2 other inputs, which makes 4 inputs for the state transition truth table. This is very similar in concept, but with just the pairing mechanism removed. So it starts at happy, gets hungry if the clock runs out. If you feed it, it becomes happy again. If from hungry it gets hungry again, it becomes sick. If you feed it once, then it returns to the previous state. And if it's sick, then if it's currently sick and the clock expires again without any feeding, then the pet leaves you or die, and it becomes game over. The transitions are quite simple. If you are at a state, then if there are no changes in the input, which means that the feeding and the expire signals are all both equals to zeros, then nothing happens. You always stay. You feed, you go to a previous state. If the clock runs out, you go to the next state, and at game over, anything happens, then you stay at game over because you can't feed or run the clock out to do anything. It just stays at game over. Um, so here is the truth table for the state transition. Zero zero is the starting state, so nothing happens. You stay. The it, the clock runs out, and you go to the next state, which is hungry. If you feed the pet regardless of the signal, then it stays. If you at the next state, which is hungry, nothing happens. Stays. Feed. You return to the previous and signals. Then you go to the next one. Similarly for all the steps. Now I'll go through the circuit design. I go from bottom to top, so the lowest level to the highest level. The lowest level I needed a XOR, so I implemented it here rather than using the gates from the circuit bus, from the circuit bus library, because it's not allowed, so I need to implement it. Next is the D flip flop. I needed to have a clear signal so that I can reset from the game over state to the beginning to the initial state, so that the user can play again if in case the pet dies, buy a new pet or something. So this is an implementation of the D flip flop with a clear signal and a preset signal, but I won't need the preset signal at all, so I'll just leave it at zero like all the time. Only need clear so that the output becomes zero regardless of the input and the clock signal. Here's just a master slave flip flop using the D flip flop that I implemented. Again, you need the clear signal to reset. Next is the timer. I use 4-bit because seems like the appropriate amount of time, which is 16 clock cycles. Here I used a NAND gate, so that an AND gate, so that whenever the clock hits like 1111, which is 15 after 16 cycles, then the clock will expire after 16 clock cycles. Next will be the main component of the entire product, which is the state transition. Here I have the signal, which is basically the expire the timer, which output the expire signal. I have fn clock and restart, so that you can restart the game. Restart will restart both the Q1 and Q0 to zero, which is the initial state of the game, 0 0. This is the logic to output the next Q1, and this will be the logic combination of logic gates to output Q0. From Q1 and Q0, we'll need to devise a this to the output of this will be a kind of display. Originally, I intended this to be a more machine because the outputs are tied to the states. But when designing the output health health display, so I found out that I need the input to synchronize the display as well as show like after feeding, then the health bar should go up rather than just staying there. So this becomes a merely machine rather than a more machine. And the RGB LED display will signal the health of the pet. This splitter essentially will show the color of the RGB LED display. So I'll just use the red. This part will show will this part will decide the color of the graph, which depends on the current state and the input. Like if you press feed, then the health bar should go up. You have more red than black, and vice versa. And lastly, you have to combine everything to get the main product. The input goes into the memory, the state transition, the state transition circuit, and then you plug it into the health circuit, connected to a RGB LED matrix display, and you'll get this. So this is when after the clock has already run out, it has expired, and you are in the game over state. So if you're game over, then no matter how much you feed the pet, it's not there anymore for you to feed, so nothing happens. If you want to play the game, then you click on restart, which send a clear signal to all the memory elements and reset it to 0. Here, so the state will be 0 0. After 16 clock cycles, then the pet's health will decrease over time, and once it's all black, then it means that your pet is gone. So once you feed, it would return to the previous step, meaning that the health bar will increase by one portion. If you feed it twice, then it will be restored to 4. You can see some glitches in the health, which is due to the synchronization between the input and the state outputs. With more time, I think I will be able to do that. But again, this is a personal project, so I had to manage my time. Considering that this is a small personal product, then I'll implement it later if I have time. So that is my product for the final project. Thank you for listening. Have a great break.